So okay, കഴിഞ്ഞ ക്ലാസ്സിൽ ഇതൊക്കെയാണ് ഡിസ്കസ് ചെയ്തത്. നെക്സ്റ്റ് we want to discuss genetic programming. Okay, we want to discuss genetic programming. Okay. Okay, so this is the flowchart of genetic programming. In this, first we will create a population, and the population consists of programs. Okay, programs. So this is important. Okay, the population consists of programs. So as I told, suppose there will be 28. Suppose all of you writing programs, and you are writing 28 programs. Okay, so suppose I want to find out the best one among them. Okay, then what I will do, I can use genetic algorithm. Okay, so here in such a situation I will encode each program as a solution. Okay, that is the initial population. Then I will apply fitness. Then I will calculate the fitness of each program. Then I will perform selection based on the fitness. Then I will perform crossover. Then sometimes I will get some other solutions. Okay, some other solutions. Then I will add to this population. This process will be repeated. In that way, I will find the best program, or I will create the best program. Okay. Then in this way, I will create the best program, or I will find the best program. This is genetic programming. Okay. So we need to consider the following issues. Which are the issues? How can encode individual solution? Okay, this is the first issue. How can encode individual solutions? Okay, so that is the first issue we need to address. How can encode the individual solution? How can encode? Okay, next is which fitness function we should use. Okay, and the third one is which genetic operators can be applied. There are crossover mutation operation. How we can apply that? Okay, these are the issues we need to address. Okay, so this is the basic approach, and we need to address these issues. So the first issue is how can encode the individual solution. Okay, so basically we want to encode a program as a chromosome. Okay, basically we want to encode a program as a chromosome or solution. Okay, so these are the genes within the chromosome. Okay, how we can encode? So basically if you consider a program, there will be arithmetic operators, standard arithmetic operators. Similarly, there will be mathematical functions. Okay, for example, sine, cos, etc., etc., seal, floor, etc. Different functions will be there. Similarly, you can notice that is in your program. Sometimes you will use your functions. Okay, you will define user-defined function. Okay, so that is called a logical or domain-specific functions. Okay, next is other related operation. There will be some other operation like this. Okay, so these are the individual components of a program. If you notice any program, these will be the individual component. So we want to encode this individual component as a gene. Okay, that is the approach we want to. For example, here I can use suppose this gene I am using for expressing the function. Okay, expressing function. Suppose this gene I am using for expressing a function. Okay, and this gene I am using to express the operator, okay, important operator used in the program. In this way I can encode a program. Okay, this is the method I want to follow, I want to use. Okay, so this is about the encoding. And so program form, also one more thing, and this is called F, capital F. uh, okay, this is capital F. These components constitute the capital F. Okay, similarly another is the program components that may include data items. Okay, so in addition to the operators, there may be there is some other component also. What is that? That is the variables used to store the data, and its data. Okay, so it will take boolean, integer, float, vector, etc. These are the different types of data we can store. Okay, so this set is called T. So basically if you analyze a program, there will be these components F and T. We will try to encode these components as individual genes, then we will create a solution. Okay, this is the method we want to use. So next, in the programming language Lisp program, component segment can be expressed as S expression. Okay, so basically genetic algorithm can be implemented using genetic programming can be implemented using Lisp program. Okay, Lisp, sometimes you may be heard about the Lisp programming. Okay, so the Lisp programming is very suitable for genetic programming. So in the Lisp program we can express the programming components as S expression. In the Lisp programming, we can express the components of a program as S expression. So, for example, then it is a very convenient way to represent individual solution work program, because various genetic operators can be applied on it to generate new program. So you can note here the Lisp program is very suitable for genetic programming. In the Lisp program you can express the component as S expression, then we can apply various operations on the S expression. Okay. For example, this is an example of encoding. Okay, so here you can note the initial population generated randomly selecting elements from F and T. Okay, so what is F? F means different function, operator, etc., etc. used. What is T? Different data type. So the individual components are selected from F and T. Then we create a tree that is called S expression. So basically you can encode a program using S expression. Okay, like this. So initially I'm selecting plus operator, then the tree will be like this. Okay, then after selection star, next I will select a star, then the tree will be like this. This is star I selected, this is added to the plus. Okay, plus. So you can note tree after selection of star as first child and 6 as second child. Okay, so it will be the tree. Similarly, after the selection of 8 as first child and plus as a second child, the tree will be like this. So in this way you can encode a program as a tree. Okay, so that is called tree encoding. Okay, that is tree encoding. Okay, basically these are called S expression. Okay, so the moral of this is that that is we can encode each program as a tree. Okay, then we can apply some operation on the tree. So here the encoding scheme is used is tree encoding. So basically we will, this is basically a program. Okay, this is the program P. Okay, we will encode the program P as a tree using the S expression concept. This is about the fitness. Next issue is which fitness measure we want to use. Okay, you already know what is meant by the fitness of a program. The difference between the program produced output and the actual result we are expecting. Okay, that is called the fitness of a program. Okay, that measure can be applied. Okay, that's a simple concept. Okay, that is the difference between what the program produced and the results that the actual task from the problem domain required. Okay, that is basically target minus actual. Okay, that can be used as a fitness measure. Okay, so this is the second issue. The first issue was, what is the first issue? How can encode? So first we discussed the concept of S expression. Using S expressions, we can implement it as a, we can encode. Then fitness, about the fitness, this is the fitness. Okay, so difference between the actual minus target. Okay, next, which genetic operator can be applied? So this is our third issue. Okay, which genetic operator can be applied? Okay, so which are the genetic operator we can apply? Okay, which are the genetic operator we can apply? So basically there are two types. You can note here, genetic operator on programs include both transformation on a tree as well as exchange of structure between trees. Okay. Genetic operator on programs include both transformations on a tree as well as exchange of structures between tree. Okay. So the transformation we are applying reproduction or crossover. So the crossover operator can be applied. The crossover operator can be applied. The reproduction is also called the crossover. Okay. So how we can perform crossover? That is the next thing we want to consider. Okay. For example, reproduction is also called the crossover. Okay, here it is defined in this way. What is reproduction? Reproduction means simply select a program from present generation and copies them to the next generation. This is called reproduction. Okay, so there are in genetic programming, and transformation operation is generally we are defining the operator transformation, which is divided into reproduction and crossover. What is meant by reproduction means simply selects a program from present generation and copies them unchanged to the next generation. Then what is so this is simple concept. Next, what is crossover? What is crossover means exchange subtree between the trees. Okay, so we know what is the basic concept of crossover. So here suppose there are two parents. Okay, but here you can note that here the parents are in which form? Tree format. Okay, so I want to apply the crossover on these trees. How it is possible? So first I will select a crossover point in this tree. Okay, so in the parent P1 tree I selected this crossover point, and in the parent 2, this is the parent 2, and in the parent 2 also I want to select a crossover point. Okay, I think I selected this is the crossover point. Okay, so you can note the first process is select the crossover points. Then what we want to do, then you can note here this is C1 and this is C2. Okay, so what we are doing is that we are applying the single point crossover concept. So what is single point crossover? This is parent 1. Parent 1's after crossover point is this. Okay, this will comes here. Okay, you can note that. That is only very simple concepts. Okay, this is the crossover point here. Then this parent wants this portion, this subtree comes here. Okay, in the C2 portion. Remaining of the C2 is unchanged. Okay, then what will be this? So from this we can create this one. And what about this? The same concept. What will be the concept? That is this portion. This is parent 2 is after crossover point. This will comes this portion. Cannot here. Okay. Remaining of the parent is same. We can note that point. So in this way we can perform the crossover on crossover operator on the trees. Okay. So basically what we are doing is that this tree is a program or a sub-program. Okay. Then on that we will apply the crossover like this. Then we will get a new program. Okay. This child C1 and C2 are basically new programs. Okay. So this is about the crossover. Then so these are the topics we want to discuss. Okay. So we addressed the issues. Okay, we discussed the various issues. Okay, one is how can encode individual solutions. Second is which fitness function we want to use, which genetic operator can be applied, and how it is possible to apply genetic operator programs. Okay, so this is about the genetic programming concept. Okay, genetic programming. So what is genetic programming? Which are the issues and how it is solved? How these issues can be solved. These are the topics. Then next just a topic is component of a genetic algorithm. So which are the different components of a genetic algorithm? So one is a set of structures that undergo transformation by genetic algorithm. So a set of structures, this is called basically the population. Okay, so the population or chromosome. So okay, set of structures, a set of initial structures. What is meant by it? Initial population. Okay, initial population. Then fitness measure. Okay, this is another component. Then a set of genetic operators to transform the structures or population. That is called crossover, mutation, selection. These are the operators. Then parameter and that describe member of each generation. And the last one is termination condition. This is also considered as a component. That is, we want to end the genetic algorithm. Okay, we want to stop the genetic algorithm. To stop a genetic algorithm, we should follow some termination conditions. That also considered as component. Okay, and the fifth one is parameter and state description that describe. That means how can encode. Okay. Okay. How can encode the solutions like that. Okay. So these are the components of a genetic algorithm. Okay. So this is the last topic of the fifth module. And so we discussed genetic programming, genetic algorithm portions. Then on the top, connectionist. So backpropagation network. So neural network we discussed. Okay, which comes in the okay. We discussed BPN architecture. So this is mainly used in deep learning applications. Okay, deep learning concept is introduced here. Then, and the first part we discussed about the various version space search algorithm. Okay, so in the first part, so what is concept learning? So there are two more algorithms we want to discuss here. I'm just explain the structure of the algorithm. Okay, as you know, the problems are somewhat complicated. So just I'm explaining the concepts only. Already I given an assignment based on this topic specific to general search. Okay. Okay. And we discussed this concept. Now we want to discuss these two also. Okay. So uh, so this is the concept space of a problem. In the version space search, what is our approach? What should be our approach? First, you create the version space of that problem using various operators. Okay. Then the version space is created. This is the most general hypothesis. This is the most specific hypothesis. Between the space between this is called the version space, and for solving a problem, we will search this space using two approaches. One is general to specific direction search. In this direction, we will search and try to find a solution. This is specific to general search. Next is a combination of both. Yes, that is called a candidate elimination algorithm. So the first case is we discussed already. General to specific search is discussed. Now we are going to just outline the structure of. So this is the general to specific search. I discussed the details in the previous class. Okay, how it performed the version space search using this example. Next is there is another algorithm specific to general search. Okay, it is similar to the general to specific. Okay, basically it will be an opposite of general to specific. Okay, so what we will do, so in the first step it's called the initialization step. Okay, during the initialization step we initialize S. Okay, this is the specific hypothesis set S to the first positive instance. Okay, S is initialized to the first positive instance in the example. Okay, next another set is N. Okay, what is N? N is the set of all negative instances C so far. So N is equal to infinity. Sorry, N equal to empty. Okay. Next, we will apply these two iterative calls. So in the first part, for each positive instance, okay, P, this is for each negative instance. Okay. In the first part, for a positive instance, what we want to check, then similar to our previous algorithm, there is a part for every S belongs to capital S. If S does not match with the positive P, replace with its most specific generalization. Okay, most specific generalizations that match P. Okay, here we are using most general specialization that do not match N. Here this is opposite. Replace with the most specific generalization that matches P. Okay, so then we will perform two delete operation. Okay, so what is first delete? Delete from S all hypothesis more general than some other hypothesis in S. So you can compare this. Okay, delete from G all hypothesis more specific than some other hypothesis in G. Okay, so this is general to specific. Here this is this top. Okay, you can compare and study. So basically, if you studied one algorithm, by reversing that algorithm, you will get this second algorithm. Okay. So next is delete from S all hypothesis that matches a previously observed negative instance. There is another step, another delete, and you can note here delete from G all hypothesis that fails to match some positive exam. Just to compare and study. Okay. Just to compare and study. Similarly, for if it is a negative instance, delete all members that match and then add n to n. Okay, add n to n. These are the steps. If you didn't include this, also no problem in the exam. And just teach this topic in exam point of view. Okay, sometimes there will be question explain differentiate between specific to general search and general to specific search. So you should write these algorithms. Okay. So here problem we discussed, but it is somewhat complex, I think. So anyway, in the university exam also, this question also only asked. So just compare and study these approaches. Okay. If we have time at last, we will discuss this problem. Okay. So it will take a lot of time, as you know, in the previous classes, we taken a lot of time to discuss this problem. Okay, this problem. So like that, it will take 1 hour. It will take a lot of time. If I have time, I will try to take it. Take it. Okay. As you know, the exams are coming on 22nd. So just study this algorithm now. So next is the candidate elimination algorithm is there. We can discuss that in the next class, and we can start the sixth module in the next class. Okay. 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 Thank you. So please give attendance. 1 minute. I will call now. Okay. So Abhilash. 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 1 minute. Please give attendance.
അവന്റെ അറ്റൻഡൻസ് എത്തി വരുന്നില്ല.
You're at. Okay, then next. Okay, next. Abhinav. Answer. Please give your attendance in the chat box. Okay, I will follow that.